Welcome to Convex Optimization. This class is cross-listed in machine learning, also in statistics. I presume you're all here for the right class. If not, you can leave now. You won't offend me. So we're going to kind of breeze through some of the administrative stuff about the course. I've heard once that the less time that the first lecture spends on the administrative material, the better the course. So we'll try to do that justice and get through this pretty quickly. Is Barnabas here? There he is, in the very corner. So this is one of your instructors, Barnabas. His last name is pronounced in a way that I can't do. Potchos? Potchos? So you'll have to ask him. I get some practice as the semester goes on. I'm Ryan Tibshirani. We're your instructors. And we have some excellent TAs this semester. Adana, I don't think, is in town yet. Is she? Yifei is in the back working the camera. Is our director. Aditya, is he here? Not here, maybe not yet. And Sashank is also not in town yet. So we have 4 excellent TAs. The course website is, as listed there, kind of the standard stuff is going to be on the course website, like homeworks. The lecture slides will go up before lecture so that you can take a look at them and print them out if you want. I'll be writing on, if I can get this light to work, I'll be writing on a piece of paper like this every lecture as we go along. I'll scan these and put them up on the website. The videos will be linked from the website, so you can find a lot of stuff there. And we're also going to use Blackboard for a bunch of stuff, so make sure you sign up for the course through Blackboard. Okay, so what about prerequisites? There's not any formal prerequisites listed in the schedule of classes or anything like that, but this class is going to be fairly quick, fairly fast-paced. So we're going to assume that you know kind of or can work with the following topics. Linear algebra and calculus, you should have a kind of a strong command of those things. You should have an idea for some of the core problems in statistics and machine learning. That's why we recommend that you've seen something like 701 before taking this class, because we're going to be talking a lot about some of these core problems, and if you haven't seen them before, number one, it wouldn't serve as very good motivation, and number two, it'd be difficult to try to learn kind of the purpose of the problem as well as how to solve it all in one course. So we're going to assume that you're familiar with kind of the core problems and why you'd want to solve them in the first place. Programming, you should be fairly proficient with programming. You can choose what language you want to program in. We're kind of indifferent. We're going to provide support for MATLAB and R primarily, so hopefully you'll choose one of those two. But if you want to do the assignments in Python, say, you're free to do that also. Data structures and computational complexity should be things that you're fairly comfortable with as well. And the last one is kind of vague, but it's also, I think, one of the more important ones, just formal mathematical thinking. You should be comfortable with kind of the idea of proving something or making rigorous arguments. Not to put Aditya on the spot, there's our TA Aditya there that I was mentioning earlier. So, okay. Yeah, so come talk to us if you're having trouble or if you're kind of worried about the prerequisites, but that's the idea. What are you required to do in the class? You're going to have 5 homeworks, 1 midterm, 1 little test. So this is going to be towards the end of the semester. It's not going to be kind of as big as the final. That's why we're calling it a little test. And 1 final project. And there's an option to take the course for 9 or 12 units. If you enroll in the 12-unit option, you have to do the final project. If you enroll in the 9-unit option, then you don't have to do the final project. So that's the difference between the units. Okay. So the final project is basically going to be about using optimization to do something interesting. It'll be in groups of 2 or 3. You'll work on it throughout the semester, and you'll start quite early. And we'll give you more details as kind of we solidify them, but that's what you need to know for now. And you're going to be required to scribe at least once during the semester. So that means basically taking notes for one class in a very detailed fashion, and then LaTeXing them and putting them up on the website. And you'll do that in a group of 2 or 3 students, and just serves as a way to kind of, well, scribe, exactly, just to keep track of what's been said in lecture at a kind of more precise level than the lecture notes. So that'll be worth a very small percentage of your grade, but it's also mandatory if you enroll in the class. All right, we have recitations once a week. There's the time in classroom, no recitation this week. Office hours, pretty much every day of the week. See the website for the office hour schedule. We're gonna have a discussion board for for you guys to ask questions and just, I guess, discuss topics about the course. That's gonna happen through Blackboard. We're hoping to set up another kind of new thing we're trying this year, which is an anonymous feedback system, so that at any point through the semester, you can provide us anonymous feedback through Blackboard. So if you liked the lecture, you could anonymously tell us that. If you didn't like the lecture, you could anonymously tell us that. If you thought a homework was too hard, you could put that up as well. Only the instructors and the TAs can see your comments, no one else, and we can't see who left the comment also. So hopefully, once we get that up, you guys will utilize that system. The purpose of that system is so that we can kind of adapt over the course of the semester to things that most of the class feel strongly about. So videos, as you can tell, this is going to be videotaped and put on YouTube, also linked off the course website. So in case you miss the lecture, you can't attend one, you can watch the videos there. And if you want to audit, that's totally fine. We don't have any requirements for auditors. We ask that you just please sign up with us instead of just sitting in. There's kind of like a formal audit form you can fill out. It's no work, but we just ask that you do that if you want to sit in an audit. Okay, and the last thing is just to work hard and have fun. Hopefully this class is going to be fun. We had a lot of fun teaching it last year. We've recycled one of the instructors and one of the TAs, but the rest are new. So I guess that's good and bad. But yeah, it'll be a fun semester. Any questions about administrative stuff before we start with the actual course content? Yeah. I'm sorry, I missed that. Speak louder. The number of units. I don't know when the deadline is, the formal deadline for that is. I'd say if you're not sure, you should at least kind of carry through with the project, because there are like milestones we've set up throughout the semester you have to complete. I would recommend that you decide fairly soon though, because if you decide not to do the project and you drop the course, or you drop the 12-unit option for the 9-unit option, then you've kind of messed it up for your partners. So I try to decide fairly soon whether you want to do the project or not. But I think you have a little bit of leeway formally in terms of when you have to choose the units. Another question over here? All right, just out of curiosity, how many people are signed up for the 36,725 number? Raise your hand. That's the statistics listing. Okay, so we have kind of a collection of students over here. How about the 10,725 number? Okay, you guys should try to mingle. You guys should socialize with each other. Don't do that next time. But okay, yeah, as expected, there's a lot more people sign up for the ML number, but the requirements for the two numbers are exactly the same. And I'd also encourage you, for your projects, you can choose your partners, but I'd encourage you that if you are have a set group of people that you always do homeworks and projects with, that you try not to use that same group for this course. Mix it up. Okay, because I mean, that's part of the purpose of taking a big course like this that's cross-listed, is that you meet people with different interests, and maybe your optimization project will lead to like a research project in the future or something. Okay, so if there are no more questions about the administrative stuff, we did pretty well. I think that was like 12 minutes. All right, so I was going to start off with this kind of high-level optimization problems are everywhere, and talk to you about army rations and MRI machines and stuff. Then I thought this sounded maybe too kind of cheesy or preachy, because I think people are kind of aware of the fact that in many facets of life, kind of there's an optimization problem being solved. So I decided to go with this other approach instead of this one, which is that they're ubiquitous in statistics and machine learning. And that's really more relevant because, presumably if you signed up for a course that's cross-listed in these departments, then you have some interest in the stats ML side of optimization. So really, optimization problems underlie kind of everything that we do and that we see, or nearly everything we do and we see in statistics and machine learning. And in many courses that you've taken so far, in these two departments, you learn how to do something like this, how to translate this conceptual problem. So this could be like, fit a function through these points or something. Fit a continuous function through this sequence of points that I drew into an optimization problem, kind of formal mathematical description of the solution to this conceptual problem. Okay, so you learn like how to make these translations, what translations are common, but you don't usually talk about this. Once you get to this right hand side, you consider it a done deal. Like, we have the solution, let's continue on. So in this course, we're going to teach you that this right hand side is not really the end of the story. There's a lot more that happens even after you pose this optimization problem, not only in actually computing the solution in practice, but also in this kind of feedback system where what you know about optimization can also affect kind of your knowledge of the conceptual problem or your choice of translation. So we're going to open up what may have been considered like a black box before and talk about how to solve this problem and what kind of implications that has. All right, so let's just start off with some examples of optimization problems in statistics and in machine learning. People have ideas? There's tons of them. What's kind of one of the most obvious ones that you might encounter? Regression, right. So, in particular, linear regression. And you guys must have seen linear regression a bunch of times. It's just you minimize this least squares criterion of a response variable or an outcome on a bunch of predictor variables or features. So that takes this conceptual idea of fitting kind of like a linear model of y on x to actually an optimization problem where we minimize the sum of squared errors of y and x times a coefficient vector. Okay, how about another example, or many more examples? What's that? SVM, sure. Support vector machines are most commonly used for classification, but they can also be used for regression also. You minimize a hinge loss in one formulation plus an L2 penalty. So I'm going to be asking questions throughout the semester, so don't be shy, because I will kind of be impatient, and I will be patient, and have the class sit in dead silence if people don't choose to answer questions. You guys know a lot more than this in terms of examples of optimization problems. Sure, logistic regression. Good example. Great. That's our statistics cohort coming through. Maximum likelihood, right? Those are all optimization problems, of which actually these two are just special cases. Mass transport problems. So that, I have to say, I don't know what that is, but that sounds to me like an optimization problem. But can you explain it to us in a couple words or a couple sentences? Great. Yeah, that sounds pretty interesting. So I haven't encountered that in statistics, but it sounds sort of like an optimization problem you'd encounter. Any other examples? Gradient descent. That's an example. So that's actually an algorithm. But how about gradient boosting? Because that's the application of gradient descent to fitting kind of like flexible models. But yeah, it's has its relationships certainly. Yeah, another good one. So model selection with AIC or BIC or RIC, etc. All these information criteria where we fit a bunch of models and then we actually optimize over those models by minimizing one of these information criteria. Okay? So how about examples of problems in these disciplines that are not optimization problems? Examples of the contrary. So this is there are a bunch of them, but maybe these are harder to think of. But like tasks you might kind of carry out in statistics and machine learning that actually aren't optimization. So what I mean that they're actually more defined by a procedure rather than a formal optimization criterion. Bootstrap, sure. So something like bootstrap or cross-validation, I might use these to select a model as well. If I fit a bunch of models, I might use the bootstrap or cross-validation to choose between a bunch of models by estimating their prediction error instead of doing using one of these information criterion. And this is not an optimization routine. I can't actually write the final estimator as solving some kind of minimization problem, for example.
Wouldn't there be any correct selection? You use as a principle of maximum scenario, for example.
I'm sorry?
In the process of this counterexamples, wouldn't you, in the process, wouldn't there be a case or a situation that you have to maximize the parameter, such, for example, interview?
Yeah, so that's a good. I think the point was that sometimes within these counterexamples there is an optimization problem, which yeah, sure. I mean, certainly there can be steps along the way that are kind of optimization subtasks, but as we see more examples, I guess the point that we're making is that some estimators or some tasks you might perform actually cannot be treated by a formal optimization kind of perspective. Yeah, so that's an interesting one. So Bayesian inference. This one is a little more fuzzy because there's a lot of optimization that kind of happens along the way, right? Even if you're not fitting something like a map estimator, you're still kind of performing optimization where you're integrating over the hyperparameters. But it's true that in some sense this is kind of less dependent on optimization than frequentist estimators. I'll give you guys some more obvious answers. Forward stepwise regression. Okay, so this is an algorithm that fits a sequence of models, right? We actually just fit a sequence of models, one of size 1, 2, 3, 4, 5, 6. And those sequence of models, they're not described as kind of solving any kind of global optimization criterion. They're just described by this algorithm, as opposed to something like best subset selection or the lasso, which also produces us a sequence of models, but those models are indexed by optimization problems. Okay, so these are estimates that are just defined by a procedure. What are other estimates that are defined by procedures rather than optimization problems? Monte Carlo stuff? Yeah, so that's a good one. So I think that goes up here with the other resampling tools. So a common one is actually clustering. So clustering usually is performed, like suppose we do hierarchical clustering. Then the clusters we get out of hierarchical clustering, they're prescribed by this procedure where we merge things one at a time. Right? But the final cluster, maybe if I cut the tree for hierarchical clustering with 5 clusters, those 5 clusters do not minimize some kind of criterion. Right? They're just chosen via this procedure, hierarchical clustering procedure. Okay, so I would encourage you guys to think about kind of where all the problems that you've seen in the past fall in terms of either optimization problems or not. And so what's the point of this? What's the point of thinking about distinctions between optimization problems and other kind of problems in statistics and machine learning? Well, one thing we're going to see throughout the semester is that often if you can pose something as an optimization problem, then it gives you a lot more freedom in various ways. For one, it gives you more freedom to solve the problem. Right? With say, logistic regression, or with linear regression, or support vector machines, etc., we can choose one of many algorithms to find those estimates. We can do them in some ways directly by solving just a linear system, or we can choose, like I said, amongst many algorithms for solving these problems. Whereas with these kind of other problems that don't fall into optimization framework, we're stuck with one. If you want to fit forward stepwise regression estimates, you have to use forward stepwise regression. There's no alternative. If you want to do hierarchical clustering, you have to use hierarchical clustering. Right? So it actually constricts us a bit in terms of the tools we have in order to find the estimates. So we're going to see an example of, just in this lecture, of how different tools can perform very differently. And that's why you may want to kind of have access to more than one depending on the problem. Okay, what's the second reason that we maybe want to study optimization problems if we can? If we can take a statistical or machine learning problem and put it in an optimization framework. It's because often just putting it in the optimization framework gives us access to a bunch of mathematical tools that also actually tell us properties of the estimates. So not only does the optimization framework help us produce a solution in practice, but kind of the mathematical framework that we learn surrounding the optimization problem can tell us something interesting about the problem in the first place. So we know a lot about logistic regression, linear regression, support vector machines, maximum likelihood, gradient boosting, model selection, etc. These things, there's a lot of literature on how these perform under various situations, for how the data were generated, for whether we place kind of regularization term on these problems. These ones, we don't know that much about. The literature on kind of the accuracy of cross-validation for model selection is very small, certainly in comparison to that for these criterion, AIC, BIC, and RIC. The literature on forward stepwise regression and kind of its performance in terms of capturing maybe the right set of variables is very, very small compared to that when we look at stuff like penalized linear regression or penalized maximum likelihood estimation. Okay, so in a lot of cases, just being able to pose it in the optimization framework actually helps us out a good deal. So those are kind of like the two motivating points that I want you to think about as we continue on through the course. I'll just say them again. I said them in the last slide in words, but here are them written down. So different algorithms can perform better or worse for different problems. Sometimes the difference is actually even drastic. So knowing the tools available is a very important thing it's very important because, it's not the case that any one algorithm is going to perform well across all situations. And the second point was that sometimes studying P, this optimization problem, actually gives you a deeper understanding of the problem you care about, that conceptual problem, because of the mathematical tools that come with being able to analyze optimization problems. Okay, here's the last reason why it's fun to study optimization. It's because it's a very current field. So it can move very quickly. That can be intimidating in the sense that the literature could change very much even from last year to this year. But it also, there's this sense of people who work in optimization that there's a lot of room for progress. So it's very exciting because, it's a very fast-paced field with lots of room for progress. And if you look at the submissions to conferences like NIPS or AI Stats or ICML or even stats journals, a lot of them are based on optimization because there's a lot of exciting things that are currently happening. And that's especially true at the intersection of optimization with statistics and machine learning. All right, so we're going to go through an example of the first point. This is a problem that whose details maybe now are not so important, but let's suppose that a scientist or a collaborator were to come to you and say that they have this data they collected. Let's suppose, just to be concrete, this person studied neuroscience. And this x-axis was time. And on the y-axis was something like the activation level of some neuron in the brain. And they measured it, and it looked like this. And they thought that as a function of time, the activation of neurons should be linear, or piecewise linear. So they apply some stimulus, and then it increases linearly, and then they stop, and it decreases back down to where it was. And then they're able to do something different, apply this stimulus in a different way, such that it increases linearly, and then roughly stays as to where, to what level that it reached. So this is the data they collected. They actually wanted you to produce an estimate of the activation level across time from this data. This was noisy, maybe it's noisy measurements because of the fact that their instruments were noisy. Maybe it's also some noisiness in the brain itself. Okay, so we're going to use a method called linear trend filtering for this problem. So this is going to fit a piecewise linear function across the time points where these changes in slope are adaptively chosen. So we don't actually have to specify the fact that we want a change point at around 200 milliseconds and around 600 milliseconds and 400 milliseconds. It's going to find those for us. Okay, and how is it going to do that? It's going to do that by solving this optimization problem that I wrote down here at the bottom. So yi are the points on the y-axis, and they're ordered from y1 on the very left to y1000 on the very right. They're ordered according to time. And the parameter here that we're optimizing over is beta. We have n of them, one for every y. And we're going to choose them to minimize the following criterion. It's going to be a sum of two parts. The first part is going to be the first part is going to be the sum over all I of yi minus beta I squared. This is telling us that the points we fit beta I at every time point are estimates. We want them to be close to yi. It's like a standard least squares loss. And this second term is going to be what's called a regularization term. In our particular instance, it's going to give us that piecewise linear fitting. So we're going to penalize basically the second differences of beta in absolute value. So let's take a moment to think about what that does. This is our criterion. 1/2 yi minus beta I squared plus lambda beta I minus 2 beta I plus 1 plus beta I. Thank you, squared. Okay, so lambda here is a tuning parameter. We're not going to talk about it. Let's suppose we just fix it at some value. And for now, that'll suffice for this example. So we're trying to minimize this, right? So the smaller the better. So let's suppose we chose lambda to be decently large. Okay, well this term is always going to contribute, it's always going to force the beta i's to be close to the y i's. What is this term going to do? Depending on lambda, it's going to have more or less effect. If lambda is really large, we're going to want to make every one of these terms small, right? Because we're trying to minimize the criterion. And in particular, what's going to happen is a lot of these terms are going to be equal to 0 exactly. We're going to be actually summing up a bunch of things that are 0, and then we're only going to have a few terms in that sum that are non-zero. Why that's the case is maybe not incredibly intuitive at this point, but we'll get to kind of all of the details of these things later in the course. Thank you, yeah. That'll be important too. So this last one is beta I plus 2. Okay, so what does it mean for this guy to be 0? If beta I minus 2 beta I plus 1 plus beta I plus 2 is 0, that's the same as saying that beta I plus 1 is equal to beta I plus beta I plus 2 over 2. Right, so let's suppose that this was time point I plus 1, and time point I plus 2, and then I'm going to draw beta here on this axis. So beta I is equal to the average of its neighbors. That's what it's saying, right? This was beta I, and this was beta I plus 2. Beta I plus 1 is the average of its neighbors. In other words, it lies on the line joining its neighbors. So the points at which that's 0, we have an exact linear relationship between those 3 points. And if it's linear for a lot of them, then we're going to get a big linear stretch. If it's non-zero, that means that beta I plus 1 is not the average of its neighbors. So when that's the case, when it's non-zero, we're allowed to do something like this. Have a kink or a knot in that piecewise linear function. Okay, so now we've convinced ourselves that this actually gives us piecewise linear fits. This optimization problem. So let's suppose we just went ahead and solved it. And again, we'll learn lots of different ways to do that as we go through the class. Here's what the solution looks like with a primal dual interior point method. Something we'll talk about kind of further on into the class. Do you have a question? Good question. So Lawrence asked, does this assume the yi's are evenly spaced? And in a sense, yes, it does. Because otherwise, this would not be appropriate, really, to penalize just purely beta I minus 2, beta I plus 1 plus beta I plus 2. We'd have to kind of divide by the appropriate differences, the appropriate distances between the input points. I's are the time points, yeah. So my picture probably wasn't great, but yeah, these were supposed to be evenly spaced. Good question. Okay, so here's one algorithm that I applied to solve this problem. It's called a primal dual interior point method. It's very fast for this problem. It basically reduces to solving a bunch of linear systems of equations. And I only needed to solve 30 of them to get this answer. Okay, so I applied 30 iterations of this primal dual interior point method, and that's what I got. And this looks quite nice. It looks believable, right? Exactly like we expect. Activation level goes up, goes down, goes up, and stays there. So we'd hand this blue function to our collaborator, and he'd be happy. He might study it downstream, or he might use it to predict new data that he hasn't seen yet, etc. Okay, let's suppose that we actually decided not to apply this interior point method, but we decided to apply proximal gradient descent, which we're going to learn fairly soon, actually, maybe in 2 weeks. Okay, well, this is what we get out of it. I did 10,000 iterations of proximal gradient descent. Not 30, but 10,000, and this is what I got. Okay, so I'll zoom in so you can see. That does not look piecewise linear at all. So at this point, if all we have is proximal gradient descent, we would wonder, is something wrong with our optimization problem? Are the solutions of that optimization problem wrote down actually piecewise linear? Is something wrong with the data? Is the data just too noisy to produce piecewise linear fits? Right? These would be the questions we'd be wondering. But in the truth, it's really the algorithm that's failing to produce a piecewise linear function. Nothing to do with the optimization problem or the data itself, but just the algorithm. And we can run it for another 20,000 iterations and it'll just barely smooth out. Okay, so this is not a good way to solve the problem. It's proximal gradient descent. Okay, and here's a third way to solve the problem. Popular tool for lots of different optimization problems currently. I applied coordinate descent, and I used 10,000 iterations, and this is what I got. Okay, so actually it's not even close to piecewise linear. It's much worse than the previous one. It's just a bunch of like noise at zero, basically. It doesn't even resemble an estimate at all of the data. Okay, so if this was our only tool, we'd be really out of luck with this problem. Okay, so what's the right conclusion here? Am I to say now that primal dual interior point method is just the best method, and I should teach that kind of throughout the whole semester, and we should scrap proximal gradient coordinate descent? Well, that's clearly not the case. Otherwise, we wouldn't teach those other two methods. But the point is that different algorithms can work better in different situations. And like we saw in this example, they can actually be fairly drastic, how well they can work. So how different they perform. So in this particular problem, there's a good reason why each of these methods performs the way they do. And once we go through the course, the goal is that you'll be able to look at a problem and anticipate what's going to work well and what's not, based on what you know about the algorithms in the problem. So this might not make total sense to you right now, but when you finish the course, you can come back to the slides and say, yeah, that makes total sense. Primal dual interior point methods, it's very fast for this problem. Why? Because the linear systems it's solving are structured. So I told you it solves a bunch of linear systems. Turns out that those linear systems are actually banded. So I'm just doing a bunch of banded matrix solves. So it's very fast. Question?
Yeah, so that regularization term over there, if I add that to square instead of using the radius, then I can get the like straightforward algebra solution that just makes zero and zero.
Yeah, that's a good point. So the point was that if I didn't apply an absolute value penalty here, but a square, or here on the piece of paper, then I don't have to use an algorithm. I can just analytically solve for the solution. And that's certainly an alternative, but that would not give us something piecewise linear. That would give us something that's actually piecewise cubic. And why that makes sense, I mean, again, I don't think you're expected to know at this point. In fact, I don't think we'll cover that in the class even, but we'll cover that the high-level idea is that different kind of forms of criterion produce different solutions. So when you have a squared penalty, none of these differences will be set to 0. They'll just be made very small. And the kind of intuitive way to look at that is that when I square something small, it gets really small. So there's less incentive to make it 0, because every time I make it smaller, it's just like it's having less and less effect. Okay, if you look at its derivative, for example. Whereas the absolute value sets things to 0 exactly. And we'll see a formal explanation of that when we go through the KKT conditions. You'll get to see that exactly that the solutions to this problem have exact zeros in these differences, but for the squared problem they don't. But then kind of the specifics of this non-parametric regression framework, why it's piecewise linear versus piecewise cubic, that's something you might talk about again in a stats class or an ML class. But good question. Okay, so to come back to our point, primal dual interior point methods, they're a good idea here because they solve linear systems, and the linear systems for this problem are structured. So they're very easy. It doesn't require kind of tough matrix algebra to solve them. It's very fast numerical linear algebra calculations. How about proximal gradient descent? Well, it's very slow in this problem, and it's actually slow because of conditioning issues. When we talk about proximal gradient descent, we'll derive a convergence rate for it, and we'll see that actually the convergence of this method depends on something like the largest and smallest eigenvalues of the Hessian, of the loss function, once we kind of parameterize it in a certain way. And for this problem, there's a very, very small eigenvalue and a very, very, very big eigenvalue, so it's very poorly conditioned. So what that means is that the criterion we're trying to optimize is very flat around its minimum. Okay, so proximal gradient descent is not going to be very successful here. It's going to take a lot of iterations. And we'll get, again, we'll kind of see a precise description of this once we talk about the conversions of this method mathematically. Chord descent. Again, so once we talk about chord descent, you'll be convinced that it's not going to even converge for this problem, so we shouldn't even try. And why is that the case? It's because chord descent requires that any non-differentiable parts of the criterion are separable. So if you look at this criterion here, these sum of absolute values are non-differentiable at 0. Right, so this is the non-differentiable part of our criterion. Chord descent requires that if we have any non-differentiable parts, that has to be additive functions of individual components of the variable. So it has to look like something like the sum of fi of beta I, where fi can be any non-differentiable functions, but it can only be a function of beta I. This is not the case, right? This clearly entangles beta I and beta I plus 1 and beta I plus 2. So we know it's not going to converge. And that's the separability concern. Any questions? All right, so one thing we'll have as a routine in the class is that after about halfway through, we'll take a 5-minute break. We probably don't have a full lecture today, but we'll do it anyway. So you guys can take a break now, and we'll resume in about 5 minutes. This is your code. Yeah, so actually, so the proximal gradient descent, I have questions about this one. No, it's maybe just too hot and your brains are fried. It's very hot. Okay, so we'll try to have discussions like this throughout the semester so you get a kind of a firm grounding for what methods work in what situations. It's an important aspect to consider. Question?
Sorry, probably not really important. You said it was banded matrix.
Yes.
I'm not sure what banded
Oh, banded,
is.
sure. Banded just means that, if I were to kind of draw a picture of the matrix for you, that it has non-zero elements in the diagonal, and then maybe kind of at some distance, which is called the bandwidth, above and below the diagonal. So it has only non-zero elements here, and everything else is zero. That's what a banded matrix is. So if I want to solve a system like this matrix times x equals b, then I can do it very quickly. Or, yeah, for reasons, I guess, which aren't so important in this particular example, but you can solve those systems. Basically, usual linear systems. So let's suppose this is an n by n matrix. If this was dense, then it would require n cubed operations about to solve. If it was banded with bandwidth k, so if this distance here, say, was k, from in any row, the length of that kind of non-zero stretch, then banded solves are O(n)k squared. So k here is 3 actually in our problem. It doesn't grow with n. So it's just linear. It's a very fast system to solve. I mean, it doesn't have to be constant. This is a complexity of a linear solve in n and k. So if k was constant, then it would be linear. If k was not constant, then it would be something else, right? But most banded systems that I don't know if I should say most, but a lot of banded systems you encounter have a constant bandwidth that's independent of the problem size. Has to do with some other aspect of the problem. So in this case, 3 came from the fact that we were looking at 3 successive points. We'd always do that, no matter how many total points we have. Okay, good questions. So here is the second example. This is an example of how sometimes the optimization framework or even the algorithm can tell you something about the problem you're interested in, statistically or from the kind of conceptual point of view. And this is a very unique example, so that's why I wanted to talk about it. So let's suppose we're interested in solving a sparse, undetermined linear system. So we were told that we got observations of the form y equals x times beta star. Y is some outcome variable. X are some features. The columns of x are maybe some features we've measured. And beta star is an unknown parameter vector. Okay, and what I mean by undetermined is that x is an n by p matrix, but n is less than p. So it's a fat matrix like this. Okay, so in general, it would be impossible to determine beta star if we knew that beta star was an arbitrary vector. If I told you that y was equal to x beta star, and x had more columns than rows, then there's not a unique solution for beta star. So if I chose beta star and I played this game where I didn't tell you and I multiplied it by x and gave you y, from y and x you couldn't tell me beta star. Because there are an infinite number of answers that would have produced that y from that x if x has more columns than rows. But now the key is that we know that beta star is sparse. Which means that many components of beta star are zero. So even though it's a linear combination of y is a linear combination of the columns of x, we actually know it's a sparse linear combination. So many of the weights in that combination are zero. Or another way of saying that is that it only depends on a few of the columns. We could have actually written it like y is equal to a smaller matrix times a smaller coefficient vector, throwing away all the columns that correspond to zero components. Okay, so this is a very basic problem that people care about in statistics and machine learning. It's a bit of a simplification of this problem because we don't usually actually exactly observe x beta. We'd even write the problem normally as y is x beta plus noise. But just for the purpose of this example, I'll take this kind of simplified view where we observe x beta exactly. But what I'm saying will carry through to the kind of more general situation too. Okay, so here's the setup, right? Y, x, and beta star. And where I put white here, it means that all those entries are zero. Okay, so the kicker is that we don't know which ones are zero. We just know that there are lots of zeros. So we want to find beta star just knowing that, you know, only a few of the variables contribute to one. So there are many, many ways to estimate beta star from this conceptual model, from this conceptual idea. I don't mean to say conceptual like it's not mathematical, it's just not an optimization problem yet. It's just an idea. And here's one way to do it, but there's literally over 10 ways to estimate beta star in this model, and take all different forms. So one way is to solve this problem. It's called the basis pursuit problem. It's very closely related to the last one, which maybe is a more familiar name for an optimization problem, but this one's called basis pursuit. So among all vectors beta that have the property that x beta is equal to y, we find the one with the smallest L1 norm. And the L1 norm is just the sum of the absolute values of beta. Okay, so again, for reasons that will become crystal clear once we talk about the KKT conditions later on, the solutions of this problem have exact zeros in beta due to the fact that we're using these absolute values. That would not be the case had we chosen to penalize the sum of squares of betas. But the absolute values actually do it for us. They set components of that solution exactly to zero. So it's going to produce for us a sparse vector beta that satisfies x beta equals y. Okay? Again, we don't know that it's going to be the one we're looking for, beta star, but it will be one that's sparse because of that absolute value penalty. So even once we write on this problem, which is called the basis pursuit problem, there are many algorithms that we could use to compute the solution to this optimization problem. And in fact, you can actually write this as a linear program, which is kind of like the simplest problem, optimization problem that you can have. And that's the one. This is the first example of a problem we'll talk about on Thursday when Barnabas is lecturing. And I'm not sure yet, but maybe for homework you'll transform this into a linear problem, so you can see why this is a linear program. So we're going to focus on one algorithm for minimizing this criterion. It's called the AMP algorithm. It stands for Approximate Message Passing Algorithm. And it's designed for pretty special situations, which means that it's designed for situations in which x has a kind of a special distribution. You can think like it's usually designed for problems in which we know that the entries of x are Gaussian, which is a fairly special situation, but it has remarkable properties. And that's why I wanted to talk about this example. So here's the algorithm. The details of the algorithm are not super important, but I'm going to go through them quickly because it's going to look like something that we'll talk about later. It's going to look, in fact, very, very closely related to something called FISTA, which stands for Fast Iterative Soft Thresholding Algorithm, which is a special type of, it's a special application of proximal gradient descent. This looks very similar to like a generic convex optimization algorithm. So we basically start with a guess for beta. We're going to guess that it's 0. And we're going to keep a residual vector r, which we're also going to set, that should say y. R0 equals y, because the residual y minus x beta 0 is just y, and beta 0 is 0. And we're going to repeat these steps over and over again. We're going to update our beta to be the soft thresholded version of our previous beta plus x transpose the residual. So what's soft thresholding? It just, we take every component of this vector and we subtract lambda from it, or we add lambda to it, depending on whether it's negative or positive. Move it towards 0. And lambda is just a parameter here that I'm not telling you what it is, but the algorithm chooses some value for it. And if we're already within lambda 0, we set the components to 0 exactly. So just from this step, you can see why we're producing sparse estimates, right? Because we're moving things towards 0, and if it's already within lambda of 0, we're setting it equal to 0 in that component. So at this first step, this is exactly proximal gradient descent. It's only the second step that differs from proximal gradient descent. Instead of taking the exact residual y minus x beta, we add something to it, which is basically the sum of subgradients of the L1 norm evaluated at our current guess for the parameter vector divided by some parameter delta times the previous residual. So these details are not important, but just know that basically this is a modification. This term is usually 0 in proximal gradient descent. It's a modification to a standard algorithm, so it's not a crazy thing to try. There's a good motivation for that step too, statistically. So there are kind of some amazing properties of AMP, and I'm talking about them at a fairly high level here, but you can read the paper that I referenced at the end of the lecture if you want to get a more precise understanding of what happens. But the story is as follows. If AMP converges, if this algorithm actually converges to some data, so after a while it stops producing different answers but just gives you a consistent beta star, then very likely, which means that under the distribution that generated the columns of x with very high probability, it gives you a solution to this basis pursuit minimization problem. So it actually solves the problem for you, which is good, that's what you're intending. But even more so, it actually produces beta star exactly. Not only does it solve the basis pursuit problem, it also solves your original problem. So if it converges, then you're great, because you solved the optimization problem and you solved the original problem with very, very high probability. If it doesn't converge, then you didn't get a solution to the optimization problem. You just got different answers at every iteration and you gave up. But that's okay, because even if you had solved this problem, it wouldn't have given you beta star. So when AMP doesn't converge, it's kind of like it's okay that it gives up, because a solution even wouldn't have gotten you beta star. And how do they prove this? They actually prove this from the algorithm. So it's the understanding of the algorithm that enables you to connect that problem, y equals x beta star, to the optimization task. So here's this picture kind of summarizing what happens. If I look at how underdetermined my problem is, the fraction of n over p. So this is the number of columns, the number of rows of x over the number of columns. And this is a very, very hard problem, right? Because I have a very small fraction of n over p is a very small fraction. This is an easier problem because they're about equal. And if I look at the sparsity of the underlying vector beta, so that's the number of non-zero components over p. So again, this is a very hard problem because, this is an easy problem because there was only, say, maybe one component of beta that was non-zero that I had to estimate. And this is a very hard problem because beta star was dense, and like we said, if it's just an arbitrary dense vector, we have no way of finding it. And through this space, I can trace out this blue curve. And on the bottom side of this blue curve, basically, I get success because AMP works. It finds me a solution to the optimization problem, and that solution is the exact answer I was looking for. This is like the easy regime of the problem. Above this curve, which means that the problem is either sufficiently underdetermined or it's sufficiently dense, I have failure. The algorithm doesn't converge, so I can run it like all the time for a long number of iterations, and this would give me kind of different answers to every iteration, but that's okay because I shouldn't have been trying to solve the problem in the first place because its solution wouldn't have been beta star. So this is a very powerful result. It's a very unique result too, and like I said, the interesting kind of thing about this example is that this is an algorithm which enables you to prove something about the problem. So it's this kind of understanding of optimization that enables you to connect back to the original model y equals x beta star.
Can you define A is the number of rows and P is the number of columns?
Yeah, so here's x, n rows and p columns, and here's beta star. It's p long, and the number of non-zero entries is k. That's a good question. So Sam asked, how is this different from the lasso? The difference is that, see, the lasso problem, just for people who are familiar with it already, but if you're not, don't worry about it. We could write it if we wanted to, like this. Minimize the L1 norm subject to the difference between y and x beta and L2 norm squared is less than or equal to t, where t is a parameter. So for any value of t, we'd get a solution that is maybe close to this, closer for smaller values of t, but doesn't assume that we observe exactly y equals x beta. The lasso solves this more general problem, I don't know where I wrote it, here, where we have an error term, right? Where we actually assume we observe x beta star plus error. And if I take the limit of lasso solutions as t goes to 0, I get the basis pursuit solution. Yes, it's a good question. This is still a convex problem. And if you believe that the L1 norm is convex, then by the end of this lecture, you'll be able to tell it's convex, because we'll talk about that shortly. Any other questions? Okay, so we'll try to talk about some examples, kind of mostly towards the middle of the course, where, in particular, the KKT conditions enable you to say things about the original problem. They tell you properties of the solution that are not obvious just from looking at the optimization problem. That's usually the main tool people use to prove things about estimators and connect them back to kind of the original model, is the KKT conditions. But in some cases, it can be an algorithm, like in this case also. The KKT conditions are just a set of optimality conditions that characterize, essentially, the solution to the optimization problem. Okay, so now moving into convexity. This will be kind of the last thing we talk about today. So you may have noticed that the title of the course is Convex Optimization. So yes, we are going to focus on, in particular, convex optimization problems. So historically, linear programs were the focus. That was where all the effort was. People wanted to solve linear programs. And they had all these applications for linear programs. A lot of them came from problems that sounded like the one you described to me, the mass transport problem, but a lot of them came from problems that had to do with kind of operations research or control, where you want to kind of, exactly like the mass transport problem or the min-cut max flow problem, they can all be cast into linear programs. So initially, after people understood linear programs, when people had a strong understanding of that, the optimization community thought the next big step that they need to take is to go towards nonlinear programs. And that's going to be the kind of the big bridge, is solving general nonlinear programs. And what was found out was that some nonlinear problems turned out to be much harder than others. They didn't look too different, but just a small change in the nonlinearity can make the problem much, much harder, and some problems much, much easier. So really the distinction between nonlinearity and linearity was not the right one. And then it was determined, there's kind of like this famous review article written by Rockefeller in 1993 that you can take a look at, but I'm sure he was not the first person to advocate this. The idea is old, and maybe there's some good references in this review article. It was determined that the right distinctions between convexity and non-convexity. That really separates the huge world of optimization in terms of what problems are kind of capable of being solved exactly, and generally incapable of being solved exactly. And if you have a general nonlinear problem, if it's convex, you're pretty much in luck. If it's non-convex, then, depending on the problem, yes, you could have great success, but there is not like a general tool to finding a global optimum. So that's why we're looking at convexity, because when you look at convex optimization problems, you can say a lot about the problems, and you have a lot of power in terms of kind of determining specific properties, finding the global optimum, a lot of choice of algorithms to use. And non-convex problems are a lot harder. We'll talk about them for probably about a week at the end of the semester, because just because something's hard doesn't mean that we should ignore it. But you'll see when we get there that we can say much less. And we're kind of betting more on local optimum rather than global optimum. Okay, linear programs, by the way, they're always convex, and we'll talk about them on Thursday, which we'll talk about. So what's convexity? Let's just cover that to get that out of the way, and then we're going to prove our first result in the class. It'll be fairly straightforward, but it'll be a nice result to have. So you've surely encountered this in another class, but if you haven't, that's fine too, because it's a fairly simple definition, but it enables us to make kind of a lot of strong statements. A convex set, C, is just a set for which if I take any 2 points in the set, and I look at the line segment joining those 2 points, that line segment is contained entirely within the set. So mathematically, that just says that if I have x and y in the set C, that means that tx plus 1 minus ty is also in C for all values of t between 0 and 1. Okay, so this is just the line that joins x and y. So here's a convex polyhedron, and you can see that actually I take any 2 points, I draw a line between the 2 points, it's entirely contained within the set. This lima bean or something, I don't know, bean-shaped set, it's not convex because if I take these 2 points and I look at, say, t that gives me, say, around that value, that's not in the set. So this is not a convex set. That's the entire distinction between convex and non-convex sets. How about convex functions? Convex functions are functions that map from some set, which we're going to call the domain of f, which is some set of Rn, subset of Rn, to the real line R, such that if I look at, essentially if I draw the function, and I pick 2 input points x and y, and I look at their heights f of x and f of y, and I join those 2 heights by a line, by a straight line, and the function always lies below that line for all values of the input along that line segment. Okay, so this is the picture. I take x and I take y, f of x and f of y. The function just lies below that line everywhere on this line segment. So mathematically, that just says that the function evaluated at the input point tx plus 1 minus ty, so that's down here somewhere, say, is less than or equal to t times f of x plus 1 minus t times f of y, which is the line segment joining f of x and f of y. Okay, so Barnabas is going to kill you with a million properties of convexity and how to check them and what operations preserve convexity, etc. These are just the definitions. So you'll hear a lot more about this shortly. But just with these 2 definitions, we can actually prove kind of a nice result, which we'll get to shortly. So what's an optimization problem? We've used that word a bunch, but here's what an optimization problem looks like formally in terms of the form. Over some set D, we're going to minimize some function f of x subject to a bunch of constraints, and those constraints we're just going to write in one of 2 ways. A bunch of inequality constraints, functions g of I, So gi of x being less than or equal to 0, and a bunch of equality constraints, functions hj of x being equal to 0. So these are our constraint functions. D is some set that we're going to take as the intersection of all the domains of our functions. So generically, D could just be the whole real Euclidean space Rn. But we could also have something like, for example, the objective function f up there. It could be a log function. So its domain could just be, some part of the. It could be like a log of some function of x. So it could just be part of the Euclidean space. Right? So we couldn't optimize over parts where it's not defined. So this is an optimization problem. Points x that satisfy x in D and also satisfy these constraints, gi of x being less than or equal to 0 for all the i's, and hj of x being equal to 0 for all the j's, they're called feasible points. That's the term we use for them. And the feasible point that achieves the smallest criterion value is called a solution. There can be more than one solution. It could be non-unique. So this is a convex optimization problem. If all of these functions, f and g of I, are convex, and we actually are going to be even more restricted for h, we're going to force hj of x to be affine in x for every j. So it actually has to look like hj of x equals ajx plus b. So provided that f is convex, the gi's are convex, and h's are affine. Some people also call this linear. I'm just using affine to make the distinction that it's not just aj transpose x, it's aj transpose x plus an offset b. Then it's a convex optimization problem. Okay, that's the general form of the problem. And like I said, you'll learn a lot more about these problems, a lot more about convexity. This is just a first pass at what it looks like. So here's the nice property of convex optimization problems that we're actually gonna show, and then that'll end the lecture, and you guys can all go home. So for convex problems, optimization problems, there are no local minima. In other words, every local minimizer is a global minimizer. And that's what makes kind of convex optimization problems so appealing in one sense, is that if we ever run an algorithm to a point in which we think we're at a solution because everything around it is bigger, then if it's a convex problem, we're done, because it is the global solution. For a non-convex problem, we could run the algorithm. It could look like everything around the point that we found is bigger in terms of the criterion value, but it could be the case that way off somewhere else in the domain, there's actually something that's smaller. So we are at a local minimizer, but not a global minimizer. And for general non-convex problems, you can never really tell. That's why they're so hard. So here's a picture. Let's suppose I had a surface, and we'll take a very simple kind of like physics interpretation of the surface. I'll just take a ball, and I'll just roll it down that surface. And local minimized will be where the ball collects, right? Because everything around that point has a higher value. And here I've drawn the criterion function, the objective function, and there are no constraints. So we just want to find the point that makes that criterion the smallest. So here's a convex surface. No matter where I start the ball, I roll it somewhere, right? From the blue, red, green, purple, or orange points, it'll get to a point, the same point, and actually that point is locally optimal because everywhere around it's higher. And we know that I can't extend this picture off somewhere else if that function is convex and find somewhere on the function that's lower than that point. But here's a non-convex surface. I can start at, see any of these points. It'll roll different directions, and it may actually settle in this crease. It may settle somewhere down here. Those are all local minima. So generically, I can't do very well with this kind of downhill algorithm with this non-convex problem. Okay, so let's just be a little more specific and let's prove this insight that convex problems cannot have local minimizers, and then we'll be done. So let's suppose that I have a point x that's feasible, So that means that it's in that set D and it satisfies all the constraints of our problem. And it also has the property that the criterion value, f of x minus f of y, I'll just write f of x actually and compare it to f of y. It has a smaller criterion than any other point that's within some radius of x in L2 norm. Okay, so if we look at any point y that's in a ball around x of radius rho, here rho is bigger than 0, then I've actually locally done the best I can. It's f of x is smaller than smaller or equal to f of y. I don't know why. I think this slide is confusing. Oh, no, this slide's fine, sorry. So this is the definition of the local minimizer. So if this is the case, we want to show that this implies that f of x is indeed less than or equal to f of y for all feasible y. In other words, x is a solution. Okay, so this is the statement that local minimizer for a convex problem, provided that f is convex and the g's are convex and the h's are affine, implies a global minimizer. Okay, so let's prove this. Very simple proof. So we're going to say, just so we can achieve a contradiction, let's suppose that there exists a feasible z and it has the property that f of z is less than f of x. Okay, then we wouldn't have found a global minimizer because z would have been smaller at least. So there's no way x could have minimized the criterion overall. Okay, so the first thing we're going to show is that if I take the point y equals 1 minus t times x plus t times z, then this is feasible for all t between 0 and 1. Okay, so we have to check basically that it satisfies those constraints, right? So how about gi of y? Gi of y is equal to gi of 1 minus t times x plus t times z, but g is convex. So that means that I can pull out the 1 minus t times gi of x plus t times gi of z and put an inequality there. That's the definition of a convex function. And this is less than or equal to 0 because x was feasible. And this was less than or equal to 0 because z was feasible. And right, these are both positive. So this whole thing is less than or equal to 0. Okay, that's true for all the gi's. How about hi? Hi of y is equal to, right, hj, I guess, just to be consistent with our earlier notation. It's aj transpose times 1 minus tx plus tz plus bj. This is actually equal to 0, just because, right, it's linear. I can pull out the 1 minus t, and aj transpose x plus bj is 0, and the aj transpose z plus bj is 0, so it's just 0 plus 0. So, okay, so yes, we've checked this. Y is indeed feasible if we take y to be the a point on the line joining x and z. They're all feasible points. Okay, so here's our picture now. X, and we said that it's locally optimal, basically in this ball of radius rho. And we have some other point out here, z, that we think actually has a better criterion value. But we've proved that any point in between x and z is also feasible. Okay, let's actually prove one more property that's very important. What happens if we evaluate f of y? then for the exact same reason, right, just from convexity, I write this as f of 1 minus t times x plus t times z. And again, I can use the convexity of f to say this is less than or equal to 1 minus t times f of x plus t times f of z. And now this is actually smaller than f of z. That's, sorry, smaller than f of x. Why? It's because f of z was smaller than f of x. Right? T was bigger than 0. So a convex combination of f of x plus something smaller than it is going to be smaller than f of x. Okay, so what we said is that we can beat x in terms of the criterion value for any point along this line. And now all we're going to do is we're going to choose that value of t so that basically we lie within this ball. Choose t small enough so that we've actually shrunken y to be in that ball, and then we've achieved a contradiction because f was supposed to be, or x is supposed to be optimal from that ball, right? So let's just compute the distance between x and y. So x minus y is equal to x minus tz minus 1 minus tx. Right, and this just ends up just being t times x minus z. Because this x cancels with that one there. So if I take x to be, if I take t to be, for example, rho over x minus c, then I'm done. Right, because I've just taken a point along this line, close enough that it lies in this ball, but that point is feasible and it has a lower criterion value than x does, which is a contradiction because x was supposed to be optimal over this ball. Okay, so just with these three definitions, convex sets, convex functions, convex optimization problems, we've essentially in about half of the page, just like a couple quick arguments, proven a very fundamental point about convex optimization, which is that there are no local minima, so that if you're doing something where you think you're at a minimizer because everything around you is bigger, then you're golden, you're done, because that's the truth. Okay, that's it for today. Barnabas will resume on Thursday with linear programs. See you guys then.